Welcome to the final video lecture for EEE 107. This is lecture 11, Receiver Design for Communication Systems. So in this part of the lecture, this part of the course, we will talk about the physical limitations of receiver architectures. And the receivers are, I believe, in my opinion at the very least, the receivers are the most important component of a communication system because the receiver will listen to the channel. It will try to identify a a signal that was transmitted, and it will try to recover that signal. So it's a key component in a communication system. Okay. A typical communication device needs a lot of different disciplines just to design it, actually. Right? You have to design your amplifiers, and that is covered by your EEE 50 series, 51 basically. Other nonlinear circuits are covered by your EEE 53. For example, for you to be able to produce analog pulse modulation schemes and digital pulse modulation schemes, you need to know how to design nonlinear circuits. And then, if we're going to be talking about digital communications, we need to understand the basics of digital signal processing. Right? And that's how you will design your digital signal processor. And then from there, how will the device interact with other devices? That will be your networks. How do you design your microprocessor, your COE115? And here, we'll focus here. How do we design the radio? Okay, the radio, you need to be able to design effective filters. You need to be able to design oscillators. You need to be able to design multipliers, mixers, and so on and so forth. An in-depth discussion are left for other EEE courses. The system level design is for advanced courses. So in this lecture, we only study a basic overview of the radio right here. Okay. What is a receiver front end? A receiver front end interfaces with the antenna. After the antenna picks up the signal, so it will be received by the RF front end. The RF front end shapes the signal and recovers the message. Okay. The functions of an RF front end can be broken down into three parts: amplification to compensate for losses, selectivity so that you won't have any interfering signals, and tunability to select your desired signal. So how do we characterize the receivers? How do we specify them? Oh, a parameter that you need to look out when you're designing a receiver is its sensitivity. What is the weakest signal level that it can pick up? Negative 110 dBm receiver, imagine how small is that signal. That is around 10 to the minus 11 milliwatts. Right? Or basically around a picowatt or so. Maybe even a femtowatt. It's very small. You need to be able to design a receiver such that it will be that sensitive. It can detect a signal that very small. Selectivity is the ability of your receiver to discriminate against adjacent undesired signals. So you have a filter for that, and you want to reject these signals that are not desired, and you want only the signal that you want to listen to, right? That's another specification that you need to look out for when designing receivers. Dynamic range is the difference between the largest undistorted input and the minimum signal that can be discerned. And this is a limitation of your amplifiers. Your amplifiers, if the signal is too large, the resulting output will have an irreversible nonlinear distortion. We studied this in the second or third lecture, I can't remember. But basically, if your signal is too large, the output will be distorted. Okay. Next is the noise figure. It indicates how much the receiver degrades SNR. A perfect receiver has a noise figure of 0 dB. That means the SNR at the input is equal to the SNR at the output. Where does this come from? It comes from what we call the shot noise of a device. Shot noise is present in active devices, basically your amplifiers and your mixers. And because of this, uh, every stage of your receiver somehow degrades the SNR after you try to detect the signal. Right? In when we were discussing the effect of noise in analog communication systems, in analog communication schemes, we did not uh, we did not what do you call this? We did not mention or we did not consider the physical limitations of the device. But if you're trying to design a receiver, then you should indicate the noise figure of the receiver, or consider the noise figure of the receiver. Okay, so let's break that down. The first goal of a receiver is amplification. A receiver has good performance with fairly strong signals that are above the receiver sensitivity. In amplifying signals, we have to keep the noise and distortion small relative to the signal power. Basically, instead of just looking at the signal to noise ratio, we also need to look at the signal to distortion ratio. We use a low noise amplifier to amplify signals, and this low noise amplifier has a property of retaining or minimizing SNR degradation. Specific design of LNA will be discussed in your communication electronics course. Number 2 is variable amplification. We want the signal, the detectable signal can typically range from very weak to very strong. The receiver should be able to adjust depending on how strong or how weak the signal is. Right? A variable gain control can be controlled using an automatic gain control where you feed back the signal and the level of the signal will adjust the gain of your variable gain control. Right? Another goal of your receiver is frequency translation. Your wireless transmission should be at a high frequency to achieve a practical implementation of the receiver, specifically the antenna. But the signal processing is less expensive at low frequencies. There's a trade-off actually. It's difficult to process very high frequencies. Why? If we want to sample this high frequency, we need to go above twice your highest frequency. And if we have a Wi-Fi signal where your FRF is 2.4 gigahertz, we will need to sample that at more than 5 gigasamples per second, and that's not practical. So we need to translate this frequency to what we call an intermediate frequency. So in this frequency, we're able to sample the signal and easily process it. Okay? So ideally, you will mix this signal with a local oscillator, and then this IF signal, depending on the type of conversion you want, the output will be this equation right here. Right? So there are two types of mixing. There are two types of mixers, basically, a homodyne mixer and a heterodyne mixer. A homodyne mixer is achieved when your RF frequency is equal to LO. That means FIF is equal to 0 if you want to down convert, if you want to translate the signal to a lower frequency. And it's a heterodyne receiver if it's not equal. That's the difference. Right. Next is filtering. Why do we need to filter the signal? I've shown you this before. Using a filter reduces the noise power at the input. Okay? And also, not just the noise, the filter actually rejects any external signal that is bothering our communication. So the receiver should be able to apply sharp filtering to remove any interfering signals, maybe in-band jammers, noise. If they are not attenuated, they tend to affect the performance of your amplifier. right? So also, the filter is used to remove any unwanted products from the mixer output. This mixer could be non-ideal. It could produce spurious signals, and we need to filter them out so that we have a cleaner signal at the output, at the input to your variable gain amplifier. Okay? So this is how it works. Say this is the signal that you want. This is, since your antenna is just an antenna, it picks up a lot of signals. It could pick up the whole spectrum right here. The job of the filter is to reject all the unwanted signals. It will be amplified here at the LNA. Then when you multiply it with the voltage controlled oscillator, this signal will be down converted here, and it will produce what we call images. These images are removed using a low pass filter here. So a low pass filter will remove the images that were born here, and the variable gain amplifier will increase the desired signal that you want while decreasing the unwanted signals near the desired signal. Okay. And with that, you're able to recover your signal. Okay. Now, let's elaborate on this image frequency problem. Okay. If you if you have an if you have a signal that you desire, you want to translate that to a lower frequency. Okay? So the problem is, if you translate that to a lower frequency, the image of this signal right here will overlap with this signal when you try to translate that. How does that happen? Oops. Right. So if you have a signal, the received signal spectrum looks like this. This is your LO. This is some interfering signal, and this is your desired signal. So I'll shade the desired signal one. Since these are real signals, then note that they have a corresponding image on the other side. Right? So if you mix that with the local oscillator, if you mix this with a local oscillator, then the resulting signal, this one will be down converted here, and this one will be placed here, this one will be placed here. Okay? This one will be placed here. This one will be placed here. As you can see, this image overlaps with our desired signal, creating interference at the output of your mixer. And this is the image frequency problem. The math is demonstrated here, but the visualization I showed you earlier. So after low pass filtering, the image and the received signal are added together, creating interference. So you won't be able to demodulate your desired signal because of the image. So to remove the image, you have to use filtering. Okay? So now let's look at the tuned RF receiver architecture. The filters are able to adjust on demand depending on the frequency that we want. Okay? And with this, by using this tuned filters, we're able to select the frequency band that we want. With this, we remove the image problem. And the more filters you put in, the better the selectivity. But it's more tedious to tune each filter. Remember, it's difficult to design an accurate filter in a high frequency, especially here, at this part where you have a high frequency. So generally, it's more difficult to design a filter in higher frequencies. That's why we have the heterodyne receiver. So we can only have, we say we have one filter only at the RF stage. And then we have the image filter after amplification to reduce the image. After this, to reduce the image before the local oscillator. After this, we look at the intermediate frequency. And using a filter again, we can reduce the interference that is experienced by our signal. And this is the use of a super heterodyne receiver. At the RF stage, you remove your image frequency, though amplification is weak. At the IF stage, you remove any adjacent frequency channel, any adjacent signal that is near your desired signal, and you can provide most of the gain before the demodulation using your variable gain amplifier. And just a note that you need to be able to tune your RF stage and the IF stage, and the IF stage and the modulation circuit here are both fixed. So basically, this this filter here selects the channel that you want to use. For example, for an FM radio, you choose a radio station, you're actually tuning the bandpass filter. But the IF filter and the demodulator are fixed circuits. And you can actually extend this to multiple IF stages so that you can improve the selectivity of your system. Disadvantages of this is the potential spurious response from your image frequency. The LO also generates harmonics when fed to a non-ideal mixer. So I told you this earlier. Can produce spurious signals. And a tunable BPF is actually difficult to realize. Okay? So for example, a superhet receiver has an intermediate frequency of 500 kilohertz, and the local oscillator can be tuned from 3.5 to 4 megahertz. The receiver is set to receive a signal at 3 megahertz. And the LO was found to have a significant third harmonic component. What are the possible carrier frequencies of the signals demodulated by the receiver? How do we analyze this? So this is the solution. The carrier frequency is 3 megahertz. So we plug that into this equation, the relationship between the local oscillator frequency, carrier frequency, and the intermediate frequency. So to get the local oscillator frequency, we can use either 3.5 megahertz or 2.5 megahertz local oscillator frequency so that we can down convert this to 500 kilohertz. However, there's a restriction here where FLO can only operate from 3.5 to 4 megahertz. Therefore, we choose the one that we can operate in. That's 3.5 megahertz. And the image frequency is around 4 megahertz. Okay? The spurious component of your local oscillator is 3 times 3.5 megahertz. It's the third harmonic, as you can see here. So the spurious frequency is 10.5 megahertz. Okay? So that would mean that your carrier frequency, what do you call this? We need to look out for for any signal at the 10 megahertz band because of this spurious 10.5 megahertz output. Okay? And we also have to look out for this 11 megahertz band, okay? Because these two could interfere with your signal at the output, okay, if you try to mix them. All right. So this is how you analyze the behavior of a super heterodyne receiver. All right. So another type of receiver is the zero IF receiver or direct conversion receiver. Basically, the signal is directly down converted to its bandpass form. Okay. So the obvious choice here is to let FLO be equal to FRF. This is also called the homodyne architecture. Since there is no IF stage, there will be no image frequency problem. For SSB, if we use SSB, well, we might not be able to reject the opposite sideband signals. So if you try to directly convert that, the interfering signal will be very close to the original signal right here. Okay. To remove that, we can expand the direct conversion to use quadrature filters. Okay. By using this quadrature filter architecture here, you will be able to remove the unwanted sidebands for your SSB. And this actually improves the selectivity compared to the architecture you saw earlier. Okay? So the problem here is that zero IF receivers are susceptible to leakage of your local oscillator. And designing a local oscillator, a non-ideal local oscillator, it's actually difficult if you want to design a pure tone oscillator. There will be spurious components. Okay? So the trade-off here is the baseband processing complexity increases, but at least your sideband can be rejected as you see here. Okay? And that's the end of this lecture and the end of EEE 107. So I hope you learned a lot for this in this course. Okay? And again, thank you for listening. If you have any comments or questions, do not hesitate to leave a comment in the comment section below. Thank you for listening. See you next meeting.